and we are working on analyzing electron energy loss spectra, and I want to do that on Colab. where's my mouse? I don't have one. So as before, we want to load all the extra stuff that we are needing. It's especially pyTEMlib. So we have an EELS tools here. We used the EDS tools before for the EDS analysis. Now we're using the EELS tools here. And we knew that we have the core loss and the low loss spectrum. So that might be even the longest thing. So it's installing it. I'm not sure why. Okay, here we go. So it's installing stuff. Maybe we should do that with the core loss already. I'm not sure whether that works. Okay. You see, we are installing that, so it would be good if you guys follow that. And hop. We install all kinds of things. If you want to know what's all in there, just set up. Okay, we are done. We don't use the Jupyter Notebook part here. And so before we run the next code cell, we have to restart our session. Okay. In the runtime menu, we always have to do that. And now we can run the widget enhanced matplotlib so that we have interactions because we want to zoom in and out. Okay. So we're done with that one. The first thing we want to do is we want to load and plot a spectrum, obviously. If you look here at your part, then you see we have the different files downloaded. And in the file widgets, we have now the option to select them. We select the aluminum low loss. You select main, and then we have here the options of how many spectra there are in. There's only one. And this spectrum we plot. Okay. If you don't set your convergence and collection angle, so this was acquired on a neon, and the communication between neon and Gatan computer is virtually not existent, so it doesn't know any of the settings, including it doesn't know anything about the convergence angle. Now, this one was actually done in the Zeiss, sorry, and it was 200 kV, and it still didn't know anything about the collection and convergence angle. So it was highly parallel beam, and it was a very small collection angle. So we have about 1 milliradian. Actually, I did some angle resolved EELS with that. So this is just the center one. Let's look at the components. Very simple. Yep. So this is our zero loss peak. Very dominant here. Okay. And if we zoom in into the smaller part here, so we have a very, very sharp plasmon peak. I don't want to do that. We have some amount of features here between the plasmon peak. So here's a surface plasmon peak and some interband transitions. We want to analyze the spectrum. The first thing we need to do is we have to shift the zero loss peak back to zero, to our origin of our energy scale. And in this case, we had to shift it by 0.13 eV. The way I'm doing that is I fit Gaussian into the tip of the zero loss peak, and the maximum of that fitted Gaussian is where I put the beam. I want to have a good representation of the zero loss peak, as good as possible. There are many different ways. So Gatan, for instance, copies the left wing of the zero loss peak to the right-hand side. Some people use Gaussians, student distributions or convolution of a Gaussian and a Lorentzian, all kinds of different forms. And I tried them all, and I didn't like any of them. And then I made a mistake, and I liked it. And this is my representation of the zero loss peak. And that is a multiplication of two Lorentzians. I wanted to convolute them, but I forgot to back the Fourier transform, and then it turned out it is perfect as far as we can see. So this is, okay, let's see whether we see the difference here somewhere. Okay, there is actually, the data is plotted here as well. Okay, here we go. So there is actually a small difference. And if we look down here, this is the difference between them. So that is the error. The error is very minimal. So we have a very good representation. The multiplication of two Lorentzians that are a little bit pushed apart. And I found that if I fit that, I can even tell which microscope it is from. So I'm not quite sure how that works. So there is not really a physical model behind it other than it works. Here is a deviation on the back side. And the question is that already a signal or not? And I must say it depends, and I would not necessarily trust that. But what we can trust for sure is at a very low energies that this is actually a good representation here. Okay. So we have the zero loss peak, very well covered. And I put all of this stuff of the analysis in the metadata of these files. So here we have the zero loss peak and the parameters product of Lorentzians. Now we are talking about the plasmon peak. So that is the other big peak that is in there. It's extremely sharp in aluminum. So this is the spectrum we have here. And we fit that with the dielectric function. And we take the loss function from the dielectric function. That is this part here. And we do the angle dependence. We had a little bit different dependence format of the dependence before. So now we are using the different energy angular dependence. So we have a logarithm, and it's dependent on this characteristic angle for each energy. This is an energy dependent part. So this logarithmic part is taken into account, and we have a constant that is dependent on various constants and intensity. So single scattering intensity is really the single scattering intensity. So that is an ideally thin sample that does not have any multiple scattering, but then in the end added to that. So we will get this single scattering intensity. So if we look at the angular dependence of that, so that's what we have here. And with the fitting the dielectric function to that, we get our plasmon peak. And that is based on this formula is based on the Drude theory, right? We had said better before, I must say. It's very broader plasmon peaks are much better represented. And okay, not quite sure what's going on, but so obviously it's not perfect here. But we get a good representation. I'm not sure what's going on. Let's try it again. Yeah, okay, so we have a small error here, but the good thing with these fits is you can always check the errors and know how much you can trust them. So now we have fitted the zero loss peak and the plasmon peak. As I said, the plasmon peak can be asymmetric due to bonding, and we also get the single scattering fit of that. But we have to look a little bit more careful. We have another peak here. As I said, okay, it's exacted twice the energy of the surface of the volume plasmon peak. There's a second peak, and that all the electrons that scatter inelastically at the plasmon, and then at some other time scatter inelastically at the plasmon again. So it's a multiple scattering. The thicker your sample is, the more of this scattering you have. So you can have 10 of those, and the plasmon peaks at that point is probably stronger than your zero loss peak. So not necessarily the best idea, but so here we have this multiple scattering one, and you can have at least 4 or 5 of these plasmon peaks that you can find. What you notice is that this plasmon peak is not as sharp as the first one. It is a convolution. So it's a plasmon peak convoluted with a plasmon peak. So it is broadened. We know exactly how that goes because this is following a Poisson statistic. Before we do that, we can also plot the dielectric function. And okay, there's a negative gone in here somewhere. That's probably a part of the problem. So what you need is the real part going through zero. So you have an eigenfrequency, and then you need to have the loss function very small so that the whole frequency is not damped. So this position in the dielectric function is really the eigenfrequency. So I didn't explain what a plasmon is, right? Do you know what a plasmon is? Okay, why didn't you pipe up? Okay. Let's explain what a plasmon is. I missed that. I normally do that. Does anybody have a cup? Ceramic one? It's a bottle. Okay. I might grab Aiden's here, but for a second. So anyway, what we need is a sample. The sample is full of electrons. So we assume here is our sample. Our electron is far away. Nothing, the sample doesn't see it. So now we make a Gedanken experiment, and since this electron is fast, put it in the center of our sample. The electron that comes is negatively charged. So all the electrons in the valence region move out. They move away from it. And now what happens is when we take it away, it's fast, right? So this valence electrons relax back, and so it makes it in a kind of an oscillatory behavior. So this is the same way as, let's see how good this one rings. Oh, excellent. So that's what I do with the valence electrons of the sample. I ring it. This one rings probably a few thousand times. A plasmon, if it is a very high, like in the case of aluminum, if it swings very, very often, so it's not limited by the uncertainty, Heisenberg's uncertainty rules, that it is very well defined in time, then it cannot be in energy. So in our case, it rings relatively long, and so we get a very sharp peak. So anything that is damped very fast, so you can have oscillations of less than one. Okay, so that would be then a very broad plasmon peak. And so the amount of how well this eigenfrequency is allowed is not damped. That is how sharp this peak is. So in our case, it's very sharp. Now we go to the multiple scattering. So this little peak that comes there, and there is actually, so that was about the first peak is around 15, so the second one is around 30, and the next one is 45, and so on and so on. Indeed, actually, a single electron can, with a very small probability, excite two plasmon because it comes in, go away, go swing, do it at some other point as well. So they have a small probability to do two of them with a single electron. So we do this multiple scattering, and I fit the same thing again, but with the probability that we had above. And then we have here the second probability. Again, it's not perfect in this sample. It's most samples, it works much better. And this is statistics that it follows. So the intensity of the nth plasmon with respect to the first plasmon, for the zero, as a first order plasmon, is a faculty of this order. It is related to T over lambda, and this lambda is the relative thickness. So T over lambda is the real thickness over the inelastic mean free path. And then it also has an exponential term in that. And since we know that it follows that, we can fit these two things onto our spectrum. And that would be the dielectric part of the valence electrons. And now we covered the main parts of this spectrum. and have that characterized. So the zero loss peak, and we have the plasmon peak. The main point is this plasmon peak does not give us much information, especially not when it's related with multiple scattering and so on. But now we have actually the single scattering plasmon, which tells us something about our valence electrons, but it's not really too informative. It is a little bit informative in terms of, it is a materials parameter. So we have, so it's very standard in polymers, for instance, to look at the plasmon peak position to discriminate different densities of plasmons, because this plasmon peak position is directly related to the electron density. The sharpness is related to how strongly they are bonded. Again, we put all these multiple scattering parameters in here as well. And then we have actually an estimation for the thickness. I would say this is it has to be taken with a grain of salt here, right? So it's an estimation of the estimated thickness. So that would be about 90 nanometer, which incidentally is quite correct, but I wouldn't really bank on that. So it's not really an excellent way for the measurement. It's a little bit better than what you're doing with inelastic mean free path, so the relative thickness times the inelastic mean free path that you get from somewhere, but not much. So we have fitted the relevant parts there. The goal is to have look at the stuff that is really interesting. So from about 2 to 4, so that is the optical spectrum. So here we don't have enough data points, but you want to look at these kind of data as well. And one way is to just fit the spectrum with a lot of parameters. So if somebody, even me, well, if you have enough parameter, you can fit anything. Then I thought, oh, if I have enough parameter, I can fit anything. So I use a lot of Gaussian and I can fit anything. And that's what I'm doing right now. I'm fitting the spectrum with just a lot of Gaussians. And we have here a difference. And you see the difference is actually quite good. And I could use a few more Gaussians, and then it fit would be even better. The problem with that is I really have no physical meaning with that. If I want to have physical meaning with fitting something, then what I'm doing is I fit the spectrum from the stuff that I don't know and don't really care too much about, possibly, and that is the zero loss peak and the plasmon peak. If I fit the spectrum minus my fit with that kind of approach, I get a very noise-free representation of the difference between that, and so the possibly the very informative data here, and this fit plus the fit that I had before gives me a nice representation of the low loss peak now. We have the multiple scattering, and we have a representation of, so this is our error here. It is reasonably small. We can discriminate it nicely. And we have we can now interpret the different parts. We have all the Gaussians to do that. You can reduce the number of Gaussians and fit it again so that you have really representative parts of that. This works extremely well, especially extremely well if you look at some plasmonic responses of materials. So if you have a monochromator and you look at the excitons, you take away the zero loss peak, you take away the plasmons, and then you fit the part in between, and you get very nice representation of this peak of your spectrum, and it also works very nicely with some noise. Why does it work? Well, I don't allow any kind of Gaussians that are sharper than the zero loss peak. That is actually my limit of how sharp a feature can be. So everything can, that is my resolution function, right? Everything has to be nothing can be sharper than the zero loss peak. So that must be then some noise. So that's a very easy way. So the beauty of a low loss spectrum is they can be acquired very fast. So they take a few milliseconds, and then you have a decent low loss spectrum. You have to take care of that the zero loss peak is not oversaturated, because you want to know exactly where the peak is. And you have to think of the low loss spectrum as a form of dielectrics. So we could fit that a bit more for that if we have separated out other features and things that are represented by dielectrics, but you really have to think of that as electrodynamics. So we get the relative thickness out of that. The absolute thickness and the inelastic mean free path are directly related to the relative thickness. So the two of them give the absolute thickness is just the multiplication of the relative thickness times the inelastic mean free path. So we get good estimates for these two parts. The plasmon frequency is very nicely resolved, right? Because we fit the peak in there. So the peak position, we always get very nice. The plasmon width gives us the damping. We can get now to band gaps. We discussed it earlier. We have some retardation processes, so Cherenkov radiation. If any of you ever looked into a neutron reactor, it has some kind of blue light, right? So the particles are faster than the speed of light in there. And so that's the same thing. So the electrons are faster than the speed of light within the material. And that is the Cherenkov radiation or retardation processes. So we have the dielectric functions that we get directly from our fit, but only for higher energies. So that is something you do not get with light, because the energies are just too high. They have a different energy range. But if you have a good monochromator, you can get to this range as well. And from that dielectric function, you get all the other parts that you need. You need to know the zero loss peak very accurately. That is now done. It might be a little bit adapted to that. Okay. Very quick run through the low loss. So now we go to the core loss spectroscopy. We go 3 p.m. core loss spectroscopy. We open it in Colab. Before I start talking, I download pyTEMlib to it, run anyway. Okay. So in the core loss spectroscopy, we remember we are looking for the ionization edges. A core loss spectrum has two other components. One component is the background, that are the tails of the plasmon peak, and of course any kind of ionization edge that lies before that. And we have many of them. So we have O and N edges that are very, very close to the Fermi level, but they are still having, of course, an energy loss that you can have, and they will introduce that before that. Okay, now we're done. We do the same thing with our runtime. We restart the session. Okay. And then we load the pyTEMlib and all the other parts that we need. So I use NumPy and matplotlib like before. Nothing much else. Okay. I don't want to connect my Google Drive right now, but you can, and then you will see that I should have done it so you can see what okay, let's see whether it works now. We had some problems before. Continue. Continue. Okay. Why does it do it twice? Okay. Good. If you look now here in the file, I have my drive, and I have some sample data. I load the spectrum. And here I just download a whole bunch of them that are in the example data. That's where I spend my date, getting this data in a binary or correct code onto Google Colab. Thanks to Boris, who put me on the right track here. So that's why we're working as a team. So what we want to look at is we want to look at a boron nitride core loss. And so you see that over here, and I select that. And what I want to add is I want to add a low loss to that. That was done at the same time. It was collected at Oak Ridge National Lab some time ago. And this is the low loss peak. I didn't select the one I wanted. I wanted to have the high loss, the core loss peak, core loss spectrum. So here we have boron and nitrogen. And if we look at the metadata, then we see a few things that are problematic. Somebody did not change the parameters, which was probably me. So we have no convergence and no collection angle. So there are two parameters that we need urgently. And we need our acceleration voltage, and boron nitride was certainly not done at 200 kV. So we always use 60 kV. So we have to adjust that. And even so, everything is recorded in the original metadata, which are preserved when we read them. In this case, if they are not inputted and if the computer does not communicate with the microscope, you have a problem. So the better integration is necessary, and I complained to Gatan for years about that, and it's not happening. So there's another problem here. This EELS spectrum is not very well. The energy scale is not correct. And in this case, the first one is correct, and the second one here should be at 400, but you see it's about 384. Actually, I think it's 386. So what we do is we change that. We change, the collection angle was 30. I'm not sure why I changed that. And the convergence angle was 20 on that microscope. And the acceleration voltage was 60. I mean the core loss one, right? Oh, interesting. So I have to have my parameters correctly, and these are the important parameters. Without that, any kind of quantitative analysis is not possible. So we have all the relevant parameters now, and we have set corrected. So we are now having nitrogen at 400 and boron at 188. So the next thing is we want to divide our spectrum by the number of incident electrons. And for that, we need a low-loss spectrum. And we have two spectra now in this dataset dictionary that we're using. And I'm using the low-loss for that. That is acquired together with that spectrum. Let's look how that looks. Okay, so it has very little intensity here, so it must be a very thin sample. Just some surface plasmons. And so we divide that just by the number of counts corrected for the acquisition time. It's a little bit tricky with Gatan how to get to that, but that is resolved in the software. So we get our intensity probability now in parts per million. So you see the maximum here is 1 parts per million. So every millionth electrons that hits the sample gets to this position here, and less than that even here. So we have to have a decent amount of counts. The metadata are here for the low loss. Okay, I didn't get any of the intensity. And the elements that I want to look at are boron and nitrogen. I left the for strontium titanate in here. So if somebody wants to play with that, then you have some pointers how to do that. So what we did now is we created the cross section for boron and nitrogen, and where this edges sit, and what I consider the near edge structure, so the parts that I don't know, the solid state effects, the band structure stuff, right? We said we only have the behavior from the cross section, so the scattering probability for the single atom. So any kind of band structure effects will not be considered. So you have, your bands are interacting close to the Fermi level, and so you have very a large deviation from your free atom, which is more like a free electron gas. And only after about 50 EV, you get rid of that. Let's look at the boron one. Is that enough? And the point is just about, right? So I want no strong features in there in the areas that I'm fitting. So everything that is having a strong feature is gone, and I'm fitting only this part here. And if I go back and do this part here, in nitrogen, I could actually go a little bit closer to the edge onset. Okay. Then I fit the data. We see now how, let's look at that, how the, so The thin blue line is our cross-section with the background, and it fits nicely here. And if we look here, strong deviations, obviously, where we have the solid state effects. And we fit that down here, and it fits, and here is our background. So nice fit, straightforward. So if we put an output of that, you remember that? Our fitting parameter was the atoms per square nanometer because we calibrated everything accordingly, right? So our cross-section is in atoms per square nanometer, so everything is here now. And we have a relative intensity of 48 to 51. So we are about 2% off in our relative intensity. The reason is the relative intensity depends strongly, of course, on your noise. And so in this case, the nitrogen was very, very noisy, right? So you cannot expect anything better than that. The overall intensity was about 15 or 16 atoms per square nanometer. And since we know that there should be about 18 there, so we have 0.9 or 0.8. So we have a 1 nanometer boron nitride layer here that we quantified unambiguously. We have 3, 4, and 5 boron nitride layers when we had that in the sample, and you can actually correlate that with that. Now we do the same thing we did with the low loss thing, low loss spectrum, right? So we have a representation of the, let's say, crude features of the sample, right? So we have our cross sections, we have our background. We want to know the shape of the edges, and we want to do that the same way. We just subtract from the spectrum whatever we fitted, and then to that we fit peaks, Gaussians. And if we look at that peak fit, there's just a few of them. We can't redo that. Where is my, here. So we did a large area here. You see we have just a few Gaussians here in that one. So if you run that in a few iterations, then the large peaks that are missing, you can still add here. Where is my spectrum? I want to go back. Okay. And so let's look at this part here. So nitrogen is very, very nicely resolved. And you can see that the signal background, signal noise ratio is in the order of 5. And so that is obviously very little. So the nice thing about that is you have now a very nice representation, and one could make it a little bit nicer than that. Here we have this green one. That is the representation of my nitrogen one. Obviously, not a lot of intensity here. It's, 15 atoms, 18 atoms of nitrogen. That is not a hell of a lot, but we still can get a noise-free representation from that. We have now a lot of peaks that we fitted. In case of titanium, edge, titanium L edge, you have the white lines. And since we know already, we know where the edges, we know where the peaks are, so we can discriminate which peaks belong to what edge. So titanium L3 and titanium L2, both of them have very strong peaks in the different materials. And now you can associate these peaks directly with these white lines, and you have a direct measure, and you don't have to do anything else. It's just the fit, and you're done. So the core loss spectrum gives us the chemical composition with higher spatial resolutions than EDS and much faster. So an EELS spectrum is in the order of 1 second. If you, for a spectrum image, you wouldn't usually do more than that. So a factor of 10 faster than EDS under normal circumstances for the core loss spectrum. And the low loss doesn't cost you any time if you acquire a core loss. The modern spectrometers can acquire the low loss and the core loss together. And so you should really do that, because it not only gives you an energy scale origin, it also gives you the number of electrons. So that's very important. And the strong background, you have to fit that. And I think fitting the spectrum is the key thing of doing that. If you do it with a nicely calibrated way, and it's standard, you can run that through many of the different spectra. You can do that through a spectrum image, and you get all the different features that are relevant. And of course, you get a noise-free representation, which you then can also compare to the literature, and possibly pattern finding is something machine learning is very good at, right? So one can even make literature search and then compare them with the different parts and see what the coordination is. Okay, with that, oh, I was very quick, but I didn't check whether there was anything in the chat. Okay. It is based, okay, so let's see. So the thickness estimation is based on the Drude theory to fit N-log term. How does it compare to the ratio method T over lambda, where the lambda is estimated from the elemental? I did not do that with the N-log term. I really did it with the multiple scattering term. So with the Poisson statistics from the single scattering to the multiple scattering ones. And so the T over lambda is very close to the T over lambda that's so the relative thickness that you normally get. But then you also get the term that is then you also get additional information about the absolute thickness that you can directly use from that. That's an estimation. So the T over lambda is, if that is any different than what you normally would calculate, it's different. And the lambda, I would strongly encourage you not to use the inelastic mean-free path from the literature. They're all estimated and calculated for rather small angles, and we use rather large angles nowadays. The accuracy, as far as I followed the literature, is about 100% for your T over lambda measurement. It is much better if you know your system and you compare that to materials that you have, of course. So relatively, the T over lambda, if you use it for the same material over and over, it's a very good estimate. it's not exact in any kind of way. Yeah, that applies also for multiple components, of course. So the T over lambda method as well, by the way. Same elastic mean-free path, that is the problem. And I estimate that with a multiple scattering fit. Again, it's not super accurate. I wouldn't trust it too much. Okay, so we're good. So that is all the ones we had. Thank you. So the next one is our hackathon. And I'm a whole minute over. I'm sorry, boys. Oh, you have a question. Oh, sorry. Okay. While Boris is setting up, I'll answer your question. Yes, please.
Yeah, in the script, like to play around with the mask, because in my case, the onset of nitrogen peak is not aligning with the...
You didn't do the energy calibration correctly then.
Okay.
So that's the problem. So the mask has to be correct. That's the only thing that you have to watch for. So very good comment. And you see, if you plot it, right, then you see immediately, hey, there is something wrong. It cannot fit the right stuff. So that is exactly the right way of doing that. So, okay, very good.
Another question. For collection angle measurements, if we don't have the calibration way of doing it, and can we do it just with the camera length and the GIF aperture measurements, or it's not accurate?
For EELS?
Yeah, for EELS collection angle, yeah.
It's a collection angle.
Yeah, measurement.
Yeah, so you go in diffraction, as you said, and just look at a diffraction pattern with the same, and then you know how big the entrance aperture, how much you see in the EELS spectrometer, that's what you see, or if you know where it is on your screens, and then you can estimate the collection angle right away. But it is something that the quantification is very sensitive to, so that is really something that has to be known.
Okay, but if we just use the camera length and the GIF aperture, so it's not accurate, like the geometric calculation.
Yeah. So what I do is I'm quite pragmatic about it. So I know what my convergence angle is. So I look at the convergence angle on my camera, and then I know what my collection angle is. So it's just whatever. 1.5 times larger, right? So it is relatively straightforward. Once you know your convergence angle, you're good. So that's what I use, right?
Okay.
Because these cameras are not very well calibrated either. So thank you.